Good evening, everyone. Am I audible? And is my screen visible? You can just write in the chat. Okay, good. So what we'll do is we'll just wait for a few more minutes and let everyone join the meeting, and then we'll continue. Yeah. So you are seeing multiple screens. That will be gone in a second. Let everyone join. I'll share my screen. Then you can see the presentation also. Okay.
Excuse me, Soumya, you have started or?
No, no. I'm just waiting for a few more people to join the
Okay,
course.
okay,
Okay.
okay. Since there was no, sound, so I thought there's something wrong on my side.
Okay.
It's
That's
okay, it's okay.
okay. Now I think we are good to go. So let's just start the session. So good evening, everyone. Myself Soumya Tiwari. I am PhD scholar at Department of Sustainable Energy Engineering, IIT Kanpur, and I'll be the TA of this course for this live session. Uh, our course is Solar Energy Engineering and Technology. Our course instructor is Professor Pankaj Kalita sir. He is also assistant professor at IIT Guwahati. And first, I'll just like to give you an overview of this course, so it will be easier for you to access the course and utilize it at its fullest. So you all might be aware about this SWAM portal from where you can access the content of this course. um, so you can see, if you log into this SWAM portal, you can see the every week content here, from your lectures to your quiz question that will be given to you weekly. And the assignment uh, due date is mentioned here, so please pay attention to the deadlines. What is the deadline, what is the time? Please submit this assignment within the time given time limit. Note that if you want to have a certification for this course, there are some prerequisite, you have to have like 25% of your marks will be taken from the best 8 assignment out of this 12 assignment that will be given weekly to you, and 75% will be your marks that will be taken accounted from your final exams that will be taken at the end of this course, that you have to give at an offline center, that you will know about later. So just a minute. Okay. Now the course content you can see from here for each weeks, in the form of lectures. The assignments are here. The feedback form is also there here, so please give some time to fill this feedback form. That will be quite useful for us. um, Please pay attention to this announcement, because um, every information regarding to this course will be updated here. The date of examination to when you have to when is the last day for exam registration, what will be your exam date and your time slot, about the hall ticket, or any information that is related to this course will be given here in the announcement sector. Okay, section. Okay. Now, in the about of course, you can see the general overview of the course. If you're just going to start this course, uh, I think we should wait for a few more minutes. I request you all to please join on time, so it will be also helpful for the student who has joined earlier. So now, so for the student who had, okay, so so for the people who have joined just few minutes ago, I will repeat the thing that I have explained till now. So you can have access to this course through the SAM portal. The weekly courses lectures you can find here, along with the assignment. um, and if you want to know about whatever update will be there about the course, you can get access to it in the announcement sector. um, uh, you can Okay, so there is a discussion forum also. So any doubt you have regarding the lecture or regarding the live session that we had, you can post here in the Q&A section. We are will be happy to answer your questions. You can check your progress here. Whatever, so weekly wise your assignment score will be displayed here. Okay, and you can track the your whatever grades you have got in particular assignment. Note that the best 8 out of the 12 weekly assignment will be added to your final marking. Okay. um, a review of assignment you can see here. As soon as you will upload your final submission about the assignment, you can see the assignment review here. So I think this is all about the course, general overview of the course, how you can access this, where you can ask question about it, where you can get the announcement or the update about the course. And I hope all of you have joined now. So before starting the session, what I would really want to do is, um, if you all are comfortable, um, you can switch on your camera or keep it, you can switch off also, that's up to you. But I just want to have a brief introduction about you also, so that I can plan this live session accordingly and we can utilize it to its fullest. So um, everyone is welcome to just give a brief introduction about them or their background, because uh, the last time I've taken this session, people are from academia to industries, to professor to students. So I just want to have a just brief introduction to you all. Hello, Alka.
Hello, my name is Sakta. I'm business partner. I'm working in management. So I'm
Hello,
working in management
Alka.
operations. Hello, ma'am.
I think your voice is very feeble. Can you please put your microphone closer, or
Okay, hello, ma'am.
hello, Alka.
I'm actually a business partner. I'm working in energy operation. So as a part of my PhD,
Sorry, Alka, to intervene here, but your voice is not clear. There is a lot of background noises.
Alka, I'm Manoj Kumar. Am I audible?
Yes, 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 you're audible. Please go ahead.
Yeah, Alka, I'm mechanical engineer and working in ONGC, the National Oil and Gas Company.
Okay,
And as a result, I understand the importance of this energy transition from fossil to the renewable side. So I'm taking interest in this course also, and then course related to hydrogen technology also.
nice. That's good to know. Because this is the call of an hour in our whole world. Uh,
Yeah.
right. Uh, so good to know. So thank you for letting us know about you. Um Anyone else want to just come up and speak?
Hi, Soumya,
Hello.
and hello everyone. Yeah, this side I'm Abhijit, and actually I'm working as senior consultant business analyst with Shell, petroleum company Shell, and I have taken this course out of my interest. And actually, I'm a petroleum grad also, so this course looks to me quite resonating. So out of my interest, I have taken.
Nice. So okay. So good to know. A lot of industry peoples are here. Uh, uh, we will curate this course accordingly only. So I think let everyone speak and then I'll. Okay. So Alka has messaged something. Uh, Alka is research scholar in Amrita and she's working in energy entrepreneurship. That is why she chose this course. Well and good. Uh, okay. Anyone else who want to speak? Yes, Sai. You can unmute yourself and speak.
Yes, ma'am. Hi, everyone. I'm Ernestella. I'm currently studying third year mechanical. I love renewable energy. I want to gain much more knowledge in it. Anything related to natural resources is my thing right now. So I hope I can gain much more knowledge from all of you. Thank you.
Thank you
Good
so
evening,
much.
ma'am.
Good evening.
Good evening, our friends. I am research scholar in MNIT Gorakhpur, Triple Gorakhpur, and I am working as workshop superintendent in Government Polytechnic, Chopan Sonbhadra.
Okay, nice.
This is my NPTEL course for research course.
Okay, so you are
Thank
taking
you.
this course for the research credit or just out of interest?
For research credit and as well as my research area is this. I want to working in solar energy in deep.
Okay, nice. 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 Good to know, Sunil.
Thank you, ma'am.
Thank you so much.
Thank you, ma'am.
Good evening. Can you hear me?
Yes, yes. You're audible, Ruchita.
Yeah, thank you. I have currently completed my fourth year in UG my third year in UG in the Energy Science Department from IIT Bombay, and this course is very relevant to my own department, so I took up this course as an elective.
Okay, nice to know that you are well aware about the trend and uh, like
Yeah.
where our
Yes.
country
Yes.
is headed. So it's very good to know that you are taking action early on and learning toward the sustainability and the natural, like
Yes.
renewable energy thing, right?
Yes.
uh, Thank you.
Good evening, ma'am. Am I audible?
Yes, yes, you're audible.
Well, hello everyone. My name is Rajesh Shashidharan. My bachelor is in mechanical. I possess two postgraduate diplomas, one in energy management and another one is in construction and project management. I've been involved in development of solar IPPs. Right now, I'm working in Qatar for world's one of the largest bifacial plot. It's an 800 megawatt peak capacity. I've been in this solar business for 8 years now, and before that, I was in wind development.
Okay, so you are already applying all the knowledge that you are going to get in this course. So it's good to know that. Uh, I hope that this course fulfills what you are needing, like in term of knowledge or in term of expertise. So it's very good to know that you are already engaged so much in this renewable energy sector.
Yeah, thank you.
Yeah, good evening,
Good
Sonia.
evening.
This is Mohammad Sikandar Hussain, working as assistant professor in Kadapa, Andhra Pradesh, and I am a research scholar in Tamil Nadu in a private university. I'm taking the course related to my research work and my project, which is I had taken the theme of regarding solar only. So I had taken the theme of solar engineering related to.
So
Thank you.
your project is sir on solar thermal application or solar PV part.
No, solar PV grid system
Okay.
regarding on and the performance analysis which are going on the PV system. So I have taken the course related to it.
Sure,
Thank you.
sir. Welcome to this course.
Thank you.
Hello.
Hello.
Good evening.
Good evening.
Good evening, all of you. My name is Santosh Kumar.
Hello, Santosh.
I'm working in Samsung Electronic for web engineer. This course I will join as for knowledge
Okay.
in Chile. Yeah.
Okay. Thank you for joining this course. Oh, I'm hoping you will be satisfied with whatever this course has been designed for. Um, Anybody else? I think I see several name: Vikas, Saujanya, Shashank, Shafiq. If you are comfortable, please come forward. It's good to know about you all. Anybody else who want to come up and tell about themselves? feel free to come up because this is actually we are not present in a physical classroom, but this is a very good opportunity for you all to come up and speak, ask your question, interact with each other. That will eventually help you to have a better learning. So I encourage you all to speak up, and it's fine if you are not comfortable right now, but I am hoping that in the later session you uh, will come up with questions, and better, you will have better experience that way.
Hello, ma'am. Am I
Hello.
audible?
Yes, yes, you're
Hello,
audible.
everyone.
Hello.
My
Uh,
name is Balark Mehta. I'm pursuing fourth year engineering, electrical engineering, and I want to do masters in renewable side. That's why I choose this course.
nice. So you are from electrical background, right?
Yes, ma'am.
Okay. So that's good to know. So thank you for speaking. Um, Anyone else? So don't worry, we'll just do this thing in the first lecture just to know you all. From the next section, we'll start
Hi,
ahead with
ma'am.
the. Hi, hi, Nanda.
I am Nanda Kumar. I am currently in second year BTech IT.
Okay,
To gain knowledge about solar energy, I have chosen this course.
okay, Nanda. So your background is in which department?
Information technology.
IT. Okay, okay. Thank you, Nanda. Anyone else? Preeti, Shashank, Saujanya.
Hello, ma'am. Am I audible?
Yes, Shashank, you're audible.
I'm 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 currently a student on final year electrical engineering, and I could choose this course for the credit transfer. And this course is also interesting because it's helping it's talking about the renewable energy. And I have one project I am working on, which is related to the generation of power by the using solar thermal energy.
So you are utilizing the solar thermal. So is it your BTech like final year project or something?
Yes, my final year project.
Nice. So your thermal application is based on concentrator or something similar to that?
It's concentration based. Concentration.
Okay,
Parabolic concentration.
okay, okay. Good to know. Because Shafiq, I think Preeti hasn't spoken yet, and
Hi, ma'am.
Hello.
Hello, hi.
Hi, Vikas.
Myself, Vikas. I'm studying in Dayanand Sagar University, now presently third year, and my department is Electronics and Communication.
Okay.
And I'm interested in this course, and I've chosen this course.
Okay. Thank you, Vikas. Uh,
Welcome.
Anyone else who want to speak, or should we continue with our course?
Mr. Vari, I believe everyone is silent, so can we start the class?
Sure, sure. So the thing I was trying to get the insight here was some people are from the bachelor background and some are not from the mechanical background. So a lot of this course has like requirement of a bit mechanical and bit electrical thing. So what I will do, I will pay close attention that I will explain well the mechanical part, so everyone um, will understand what we are trying to tell. Um, I hope everyone has gone through all the lecture of at least week one, right? Can you just quickly
Yes.
write yes in the chat box?
Yes, ma'am.
Okay, Rajat has raised his hand. Yes, Rajat, you can unmute yourself and speak.
Sorry, my apologies. It was by mistake.
That's fine. Okay. So note that the assignment deadline is on the 7th of August for the both week one and week two assignment. If I'm not wrong. So what we'll do is, as you have, okay, let me check. Okay. So I hope that you all have gone through the week one lectures. So what I'll do is I'll quickly go through the content of this week. So if someone has not seen the lecture, they will get like they will have a little insight about it, and then we'll quickly go to the questions. So what I'll do is I'll show you the question. I'll give you some time to answer those question in the chat box, and then we'll discuss the answer of that question. Okay. So this will be going to be the format of this live sessions. Um, so let's start. So in module 1, week 1 lectures, the content of this module was basically discussing about the energy scenario in the world, talking specifically about the India, how solar energy is playing a vital part into the this upcoming energy requirement. So sorry to interrupt. I think so. I request you all to please join on at the given time. So the session will not be interrupted again and again. So I expect that from tomorrow you will join um, at the appropriate times. And okay, so lecture 3 discussed about the physics of propagation of solar radiation from sun to the earth. So this whole live session will have question related to these three lectures only. So the lecture one was just the introductory one. I'll just start from the lecture two, where solar energy conversion devices and its application were discussed in details. So there are different mode of exploiting solar energy. So you can ideally use its thermal part, or you can convert solar energy into electrical form and utilize that energy. So if you are going for the electrical part, then solar PV modules are solar cells are utilized. uh, and if you are going for the solar thermal application part, then you can directly use the solar energy to heat particular fluids, and then basically at a lower temperature you can use it for various application like solar cooking, solar heating. And if you use concentrator, where intense heat can be generated, that is enough to drive the turbine, then you can again generate the electricity, and that will be useful for, in the large power stations. Now, this is just to give you example about the solar thermal and solar um, PV application. So, uh, you might have seen the solar collector on the roof of your house, or not in your house, but in several municipal corporation and all. So, where you have the solar collectors with pipes in which the fluid is flowing, the solar energy is hitting the fluid in these pipes, and this heated hot water can be utilized for further application. Similarly, solar PV are more common than this solar thermal part right now. So this PV solar panels could be seen at various rooftops, where its solar energy is converted into electricity, which can be utilized for in-house applications, or it can be also like the excess electricity can be also be supplied to the grid, and on grid system could be also there in solar PV part. So the direct method to solar energy utilization is the thermal and PV part, as discussed earlier. The indirect method is the water power, the wind, the biomass, wave energy, marine current. So it's all indirect ways of utilizing this solar energy. Now coming to these devices are very important, because this will be also discussed in detail. The numerical question will be framed on these devices only, so you have to pay attention to the working or the numerical aspect of these devices. So depend on how much temperature you can reach. So liquid plate collector is a very basic solar thermal application device, where you can get temperature up to 40 to 100 degrees Celsius. So this is the flat plate collector. And okay, so this is the flat plate collector, and evacuated tube collector. This figure you can see, where this is better than the liquid flat plate collector, because vacuum is there, so that prevents heat loss. And the basically performance of this device is better than the liquid flat plate collector, so we can get temperature up to 130 degrees Celsius. There is solar air heater, where you can get the temperature around 90 degrees Celsius. Then you have cylindrical parabolic concentrating collector, where you can get temperature up to 400 degrees Celsius. And your parabolite concentrating collector, where you can get temperature more than 400 degrees Celsius. So you need to be aware of what is the application, up to which temperature the particular thing could be utilized. So the application part is quite clear in your head, right? So this slide basically tells about the construction of a liquid flat plate collector, where you can see these pipes in which your fluids is flowing, and this is the glazing sheet through which solar radiation passes, fall onto this pipe, where it gets heated. It in turn heats the fluid flowing inside it, and you can finally get your hot water out. And this is very simple in design. There are no moving part, very little maintenance is required. So this is a very simple application, but very useful application of solar thermal energy. Now in evacuated tube collector, rather than having a single pipe, what we have is a you have two concentric pipe, in which the inner pipe where fluid is flowing, and this is the vacuum that has been maintained. and the solar radiation are falling onto this outer tube, passing through this vacuum to the inner tube, where the in turn it's heated the fluid flowing inside this pipe, and this fluid is then again uh, uh, used in the heat exchanger to heat various whatever fluid you are depending on application. So this is this its performance is better than the flat plate collector due to the vacuum that has been incorporated into the design, that prevent the heat loss to the surrounding. Now solar air heater, as the name suggests, solar energy is utilized to heat the air. So somewhat similar design, insulated structural container is there in which the air is fed, and glass cover is there from which the solar radiation are passing, falling onto the absorber plate, which in turn heated the air inside the container, and your hot air can be further um, uh, we can get the hot air for various applications. So we have to keep, while designing it, we have to keep how much volume of this container should be, so there should not be a pressure drop. It should be in the manageable limit. So this all things will be discussed in detail in the upcoming weeks also, so it's just here to give you a glimpse of all the devices. Now this is the cylindrical parabolic concentrating collector, where you can reach temperature up to 400 degrees Celsius. So this is the tube uh, where your fluid is flowing. This parabolic curvature is there on which the solar radiation are flying, basically concentrating, and this is further concentrated onto this line. So this is a line focus type solar concentrator, where all the falling radiation falling on this trough is finally concentrated back onto this line, along this line in which your fluid is flowing. So in this, as the sun changes its position throughout the day, what happens is it's generally solar tracking is required in this type of devices. So throughout the day it changes its orientation, and so that at all the time maximum utilization of this device could be there. And this is the solar disk or paraboloid concentrating collector, where we can get temperature greater than 400 degrees Celsius. It's basically used for high energy and applications, where the temperature generated could be very high. And this is similar to the central receiver concept, where we have dish, and radiation are falling onto dish, getting concentrated on a point. So this is point concentrating type of solar thermal device. So the whole radiation is concentrated at the point where your heating application is done. Now this is the I think the numerical sir has explained in the class. uh, I hope everyone has understood this numerical. If you have any doubt in this numerical, I can explain it again. Otherwise we can skip also, as you say. Okay, still sees. Okay, Manoj, I think I see few hand raised. Manoj.
No, ma'am. I had raised earlier for some other reason, not now.
So is there something you need to ask right now?
No, no, not now, not now.
Okay, fine. So what I will do is I will quickly give an overview of this numerical. So there was this flat plate collector on which solar radiation are falling, in which water is being heated, cold water coming in, hot water going out, and 100-liter capacity thermosiphon solar water heater is there. So solar radiation was 5.5 kilowatt hour per meter square, with collector efficiency of 52%, and absorber area was just a minute. So this absorber area was 2 meters square. Water inlet temperature was 23 degrees Celsius. Atmospheric temperature, specific heat of water is given, geyser efficiency is given, and unit cost of electricity is given. What has been asked is what is the temperature rise and what is the saving of monthly electricity bill, right? So just a minute. Okay. So 5.5 kilowatt hour per meter square. So and the area of absorber is 2 meter square. So the energy that has been falling on this whole area will be 5.5 into 2 kilowatt hour, right? Now this collector efficiency is 52%. So only 52% of the uh, falling energy or in term of radiation is being passed on to this pipes or the collector tubes, right? So the actual amount of energy that has been going is 5.5 into 2 into 0.52, right? Now geyser efficiency, this much energy is used to heat this water. Now if a geyser is being used uh, to heat the same to heat the same amount of water to the same temperature with 96% efficiency. So the actual amount of energy that has been actually saved will be we will basically divide by 0.96. Hope this part is clear. So the actual amount of energy saved per day will be 5.72 kilowatt hour, and 1 kilowatt hour in unit cost of electricity is 6. So for a day you have saved 34.5.72 into 6, so it will be 34.32 rupees, and monthly I think you have saved into 30 will do. So 1092.6 rupees has been saved on your monthly electricity bill. And if you want to know about the temperature rise, mcp delta t, this so this much energy is utilized to heat the water. So like um, we are talking about specific heat. So mcp delta t, hope you are aware about this uh, basic equation. So the uh, energy will be, sorry, but please bear with me. M, and this is the mass, okay, and this is the specific heat of water, and delta t is the change in temperature, right? So this much energy is required to change the temperature. So you have it's given in the liter. cpu has been it has been already mentioned, and t in is 23 degrees Celsius. We can basically tc is given 23. So you can equate it with this energy and basically can get outlet temperature of the hot water, which will come around 72.26 degrees Celsius. I hope this numerical is clear.
Hello.
Hello.
In this case, I want to know its gauger efficiency is 96%.
Right.
That we are dividing. Rather, it should have been multiplied, I think, because the gauger efficiency if it comes down, then the saving power will be increased.
So you can understand it in this form. So um, from electricity, whatever, if you want to rise the temperature from 23 degrees Celsius to 72.26 degrees Celsius, some energy is required, right? So that much energy is provided by, if you are saying using, if you are using electricity, so only 96% of uh, geyser efficiency is 96%, right? So say if you are going for if say 10 joule energy, say just for example 10 joule energy is required to heat the water, okay. Now the actual requirement of energy will be, since its geyser is only 96% efficient, so 10 by divided by 0.96 will be the actual amount of energy that has been used by the electricity, right?
But if the geyser efficiency comes down, if it becomes 70% or 50%, then saving per day that will be more.
Right. So if your geyser is not efficient, so much efficient, so it is requiring the actual required, right? So that much energy or that much in term of cost is being saved by your solar energy. Anyway, to
Okay, it's
raise this
reverse.
temperature, some amount of energy is required. So if geyser is not so much efficient, more energy will be utilized to heat the water temperature to the same degree, right? Hope
Yes, sir.
you have understood what
Yeah,
I
okay.
has been tried to say, right?
Okay.
Any more doubt?
And one more thing that TH got 22.266.
Sorry,
TH we got 0.26 degrees centigrade.
your voice is not clear. Can you please tell again?
Then in the other thing, in that question, the other part of the question is saving in power, that is okay.
Right,
The other part, what you told just now, that the equation you told one equation there,
right,
but got that TH is equal to 72.26 degrees centigrade.
right.
That how you got? That again, please
So
tell.
that this much amount of energy is basically used to heat to rise the temperature of water from 23 degrees Celsius to a certain temperature. So that temperature you have to find, right? Rise in the temperature. So you can simply use the this formula where the energy utilized will be equal to m mass of the water into Cp, specific heat of the water, which will be in kilojoule kg per Kelvin, and delta T is the rising temperature. So it will be the T higher minus T lower. So T higher is the what you are have been asked in the question, and T lower or T uh, cold water temperature is given already in the question, 23 degrees Celsius. If you put all this thing into this equation, you can directly get the T higher value.
So how it is coming, madam? M is equal to 100 liter.
So
100.
100 liter you have to again convert it into, it's in kg, right? Per specific heat of water is given in kilojoule per kg per Kelvin, right? So it's and the mass is given in 100 liter volume is given. So you have to first convert into kg, and then basically 100 liter into 10 per.
100 liter means it's coming 100 kg. 1 liter is 1 kg. 100
Huh,
liter is 100 kg.
hello,
Hello.
right,
1 liter is 1 kg. So 100 liter is 100 kg into
right,
CT.
right.
CT is
Cp is
specific.
4.18 kilojoule per kg Kelvin,
Acha, 4.18
right?
into delta T. That delta T we require.
So this will be 100 into 4.18 into you have changed in the so basically this will be, so I don't have my pen right now, otherwise I would have explained it.
E will be 5.72. E is
uh,
equal to delta T. Na? Delta T you got.
Delta T will be basically th minus your 23. So
Yeah.
you can keep it in Kelvin,
Yeah,
273
yeah.
plus 23, so it
Okay.
will be 300. So it will be basically th minus, basically th minus 300. uh, this will be basically delta T, okay?
Okay. And
So when you will solve this, you will get the answer. You can solve it by yourself. If you have any doubt, you can ask again, or you can go back to the lecture also. Sir has explained it very well. I'm
okay.
just giving you the gist of the question, okay?
Okay.
Hope everything is clear. The basic understanding of this question is clear. The calculation part you can do it by yourself, right? Okay, I think we should continue. So the thermal application part is various applications are there, from water heating to space cooling and refrigeration to power generation to distillation, uh, to drying and cooking. So these are all things that has been explained in detail in the lecture also. You can go back to it. Just a minute. Okay, someone. So this is one of such example. So this is called solar distillation. So this is the glass cover from so solar radiation are passing. So it's based on the water cycle that we have read in our childhood. So what happens is solar thermal energy is used to heat this impure water. The water vapor rises, it condenses on the glass, trickles back, and then we can collect this pure water. So it's a very basic application of this thermal application of this solar energy. And similar is this air heating, where sunlight is passing through the glass, heating the air, then we can basically channel this hot air into particular application zone. And solar cooking, you might be aware, where solar energy is reflected into the box, and some solar energy are directly hitting these spots where food is contained, and it's black coated to increase the absorption of the solar energy. So these are the various, there are various thermal application of the solar energy. uh, Now coming to the solar uh, electrical part. Okay, so in a solar electrical part, what we are doing is, with the help of solar panel or solar cells, we are directly converting solar energy into your electricity, and then you can further uh, produce it, store it, transform it, utilize it according to the application. So there are two major families of PV generation. One is standalone system, and one is grid connected system. So a standalone system just mean that whatever you are generating from PV modules, um, you are it's off grid system, right? So you are utilizing it for your in-house application purpose, or storing it for your in-house application purpose. So basically you have your PV module on which solar radiation are falling, DC current is generated, inverter is used to convert into AC current. And basically you can utilize it further depending if you are using it for pump. So basically you can use in conjugation with the motor generator system, and where we can have a solar pump for our distribution purpose, right? So and we can use it with battery or without battery, depending on your application, right? In hybrid standalone system, so PV plus diesel generator both are being used. So you are generating electricity by the PV system also, and you are generating electricity by your generator only, and you are storing both electricity into your battery, and based on application you are utilizing that basically electricity. And in grid connected PV system, you are connected to the grid, so the surplus energy, electrical energy, or you can say electricity, is then given back to the grid. And in case of the requirement, or um, when your PV system is not working, or say in the night, or say in the off season, you can take electricity back from the grid as per your requirement. So this whole system will be discussed in detail in upcoming lectures. Here we are only giving an overview about all the devices, or the solar application devices. Now the storage of this energy, so it could be a thermal, electrical, mechanical, or chemical form. Thermal energy, as we have seen, sensible heat storage, where we have heated the water, try to increase the temperature of the water, and then utilize it further. Or you can use in the latent heat storage form only. So phase change material could be used, like paraffin wax and all. So later what they do is, while they absorb the energy, change their phase, and later in the night, where solar energy not there, say, so they will change back their phase to solid form, and they will again release the heat in the night, and that can be used for the continuous application purpose. So and some novel devices like solar ponds are also there. So this will be also discussed in detail later in the upcoming lectures. Electrical form, you have already seen solar PV or solar cells are used to directly convert into electrical form, where it can further stored in the electrical batteries. Mechanical part, compressed air system, flywheels are there. Thermochemical storage, that is very upcoming topic for the research also, where solar energy is directly uh, utilized to generate solar fuel. So what is solar fuels? So those are more cleaner alternative, greener fuels, that are used can be used in the alternative to the fossil fuels that we are using. So we are utilizing solar energy into several endothermic reaction, where we can produce um chemicals like hydrogen or syngas, or several other chemical products, which can be further utilized to get energy, instead of the using your fossil fuels. Okay, so this slides is tells about the solar power plant. Low temperature power generation using flat plate collector, medium temperature using cylindrical parabolic concentrated collector, and high temperature using your central receiver system. So you can see that your solar trough is placed here, which is used to basically heat the cold water into hot water, and it can be further used in the turbine generator system to basically further steam is generated from it and fed into turbine generator system to generate the electricity. So you can go through the lectures. Okay, so here solar power plant in India. So this slide explains what are the major solar power plant in India. This slides are like the data date back to the 2018 and 19. Um, so the largest PV plant in India is Pavagada Solar Park. This is in Karnataka. 2050 megawatt plant will is there, and some Gujarat has Chanak Solar Park 615 megawatt. Uh, so these are the major largest PV power plant in the India. This you can go by yourself, have some practical overview about what's the case of solar power plant in the in India in the current scenario also. Okay, so since we have 1 hour, I think 1 hour left. So what we will do is slowly will I will show you the questions, and you can write the answer in the chat box, and then what we can do is we can discuss this. So these are the very basic questions. So I have taken a question from the week 0 assignment, because that mark is not going to be considered in your final test numbers. So I have included that question, and I have also included some question based on week 1 lectures. Okay, so just to give you insight about what type of question could be framed, and I'll explain it the answer of this question in details. And Okay, so let's start that. So this is the first question. What you can do is you can all write in the chat box the correct option corresponding to this question. So I'm seeing different answers. Option B, A, and C also. Okay. So okay, let me see the answers. So Sarge has voted very highly for B option. I can see lot of B's there. Okay, so some had told infrared also, and okay, B option, and A option. Okay, anybody else? Okay, so the correct option for this question is B, visible radiation. Now, so you can see the electromagnetic spectrum here. So from ranging from your gamma rays to radio waves, and corresponding wavelength for each of this different spectrum. And if we'll see the zero point 0.4 micrometer to 0.7 micrometer, so basically you can see this correspond to somewhere I have written also in the table for better understanding of the values. So you can see that the range lies in the visible region. So ultraviolet radiation, A option, and C infrared radiation are not quite stable answer. So I hope this question is clear. You have to, I think, remember the few wavelength value that are important, that might be relevant for this course. So like the visible radiation spectrum, that value you have to keep in mind. Okay, so moving on to the next question. So this question is, which of the following expressions relates correctly the energy of photon of sunlight with wavelength? So there are four options given. This is the very basic question. I hope I will get answer to this question from all of you. Again, I will give some few minutes. Please write your answer in the chat box. Okay. Okay, so lot of D option. Okay. D. Okay, some has opted for D, A, and C also. Okay. Well, let's discuss this question. So the correct answer for this question is uh, the correct option is option A. So E equal to hc by lambda, where E is the energy of the photon, h is the Planck's constant, which value is 6.626 into 10 to 1 minus 34 joule per second. C is the speed of light, which value is 3 into 10 to the power 8 meter per second, and lambda is the wavelength. So E is inversely proportional to lambda. So higher the wavelength, less will be the energy, right? Corresponding to that photon. So I hope this question is clear. Equal to hc by lambda. So depending on wavelength, your energy changes inversely. It's inversely proportional. Okay. Any doubt in this question? Okay. Should we move on to the next question? If anyone have any doubt, you can unmute yourself and ask straight ahead. Okay. Now the next question is a hot object of temperature T1 is placed in a vacuum chamber having a cold wall at temperature T2. Now the hot object cools as a result of heat exchange by which mode? So is it by conduction or convection or thermal radiation or evaporation? the most of you have answered uh, option C. Okay. The correct answer to this question is option C. It's by thermal radiation. Um, as you all know, there are three modes of heat transfer. One is by conduction, one is by convection, and another one is by radiation. In conduction, we need to have a direct contact to transfer the heat. In convection, there is involvement of some fluid. There is involvement of mass motion of the molecules for energy transfer, like air flowing on the top of a hot plate. And in radiation, it does not require any medium for heat propagation, uh, and it is basically done by electromagnetic radiation. So in a vacuum chamber, uh, there is a heat transfer between a hot object to a cold object by a mode of uh, thermal radiation, heat transfer mode. So I hope this question is clear. All right. So the correct answer is thermal radiation. Now, uh, this is the next question. The question is, which of the following law provides the rate at which energy is radiated by a black body at a given temperature of T Kelvin? So I can see option C, option D, Anyone else? Okay, so most of you answered option C. But let's discuss this question also. So, we are talking about the law that provides us with the equation that tells about what. Okay, just a minute. Fine. So, which of the following law provides the rate at which energy is radiated by a black body at a given temperature of T? Okay. So, the correct option for this question is option number C, that is Stephen Boltzmann. Okay. So, the Fourier law tells us about the conduction, where the Q is the rate of heat transfer is directly proportional to area and your temperature gradient. Okay. So it's q equal to minus k dt by dx. So this is the temperature gradient across the length along with the heat conduction is taking place. Okay. Convection, Newton's law tells about the convection. Okay. So where rate of heat transfer is directly proportional to area and the temperature difference or the temperature gradient. The Stephen Boltzmann law talks about the radiation, where it states that the rate of heat transfer is directly proportional to area and the absolute temperature of the black body raised to the power 4. So this is the equation that we are talking about, q equal to sigma a t to power 4. So Stephen's law, Boltzmann law is uh, the basically law that provides this equation. The option D is the Bogus law. It's basically tells about how much, if a light is passing through a medium, how much energy of this rays has been absorbed by the medium or has been transmitted out of the this particular system. So absorbance is given by epsilon L into C, where epsilon is the molar attenuation coefficient or absorptivity constant, L is the optical path length, and C is the concentration of that particular medium. Okay. So I hope all options and the correct option for this question is clear for this question. Any doubt in this question? Okay. Okay, moving on to the next question. This is a basic fluid mechanics question. Uh, the kinematic viscosity of fluid is equal to, so it's a relationship between dynamic viscosity and fluid density. So you can work it out. Just tell me the right answer in the chat box. Okay, I can see a lot of you have answered option A. Right. Okay, Prashant is asking, can I get your recorded class session in later? Right. So Prashant, the slides as well as the lecture will be provided to you. Every lecture will be provided to you. The link to this lectures will be uploaded on YouTube, and you will have the link to that YouTube videos. Everything will be provided to you. You don't need to worry. You can watch this session later also, ask the question in the next session regarding to this session, or you can ask in the direct discussion forum also. Okay, so I think we should discuss now this question. um, so the correct option is option A. So kinematic viscosity is mu by rho. It's another way of representing viscosity. It's basically resistance to the motion of the fluid, and used in the flow equation, its unit is meter square per second. And basically, this is your relation between dynamic viscosity and kinematic viscosity. Okay. Now, this is another important question. Reynolds number. Uh, what is the mathematical representation of Reynolds number in term of ratio of viscous force to inertia force, or inertia force to viscous force, buoyancy force to inertia force, or buoyancy force to viscous force? Okay, a lot of you have answered option B. Any other guess? Okay, let's discuss this question. So, I think we were here. Right. So, Reynolds number is the ratio of inertia force to viscous force. That is option B. So, I have pardon here. So, Basically, Reynolds number is a dimensionless number in fluid dynamics, where based on the Reynolds number you can tell whether the flow is laminar or turbulent, and it's basically ratio of inertia force to viscous force. So let me just correct here. So it's option B. Okay. Or you can, in a simplified form, you can uh, write it in term of density of the fluid into velocity of the fluid into characteristic length of the solid in which the fluid is flowing, uh, divided by its dynamic viscosity. So these are the some of the important dimensionless number that you have to keep in your in mind, right? So the next question is, for a closed system, the difference between the heat added to the system and the work done by the system is equal to the change in whether it's enthalpy, entropy, temperature, or internal energy. Okay, so we have got option D and option A, and I don't know why Sarag has opted for all the option A, B, C, D. Okay, we have got option D, right? So most of have you on answered option D. Okay, let's get back to the question. So this is a basic thermodynamic question where this question basically talks about the first law of thermodynamics, right? And the correct option is internal energy. So the first law of thermodynamics gives the relation between internal energy, work done, and exchange heat. So the net amount of heat and heat basically uh, net amount of heat into the system or out of the system, and net amount of work done by the system, that is equal to the change in the internal energy of the system. So delta U is the basically designated sign for internal energy. So change in uh, internal energy given by delta U, that is U2 minus U1, if the system is going from uh, one state to two state, that will be the change in internal energy will be equal to the net heat or the heat added to the system and the work done by the system. So Q minus W. Okay, so note that the signs designation for heat in is the positive, heat out is negative. Work done by the system is designated by positive sign, and work done on the system is designated by the negative sign. So that's why this that's how this equation arises. Okay, whereas enthalpy is basically your heat transfer between system and surrounding during a chemical reaction or at a constant pressure. So basically change in your enthalpy will be equal to mc delta T. Okay, or in terms of, if we talk about a reaction, then it will be um, uh, basically enthalpy of the product minus enthalpy of the reactant. For an endothermic reaction it will be positive, because heat goes from surrounding into the system for an endothermic reaction, and for an exothermic reaction heat is coming out of the system. Okay, so delta H will be negative. If we're talking about the entropy, what is entropy? It's basically a degree of randomness into the system, in the system. So lower the entropy, more ordered will be the system. Higher the entropy, more will be the randomness within the system. So I hope this question is clear. Since we have running out of time, we have only 15 minutes left. I will quickly discuss all the questions here. So next question is based on cyclic heat engine. So a cyclic heat engine operates between a source temperature of 800 degrees Celsius and a sink temperature of 30 degrees Celsius. The Carnot efficiency of the heat engine is. So you can quickly do the calculation and write in the chat box the correct answer. Okay, so most of you have answered B. Shravak has answered all the options. So Shravak, could you explain why you have opted for all the options? Can you please explain? Or is there some hardware malfunctioning going on in your system? Okay, so I'm seeing here option A and B, right? Okay, so let's move ahead. So the correct option for this question is option B. That is 71.76%. Okay. So engine is basically cyclic heat engine is operating between a high temperature source and low temperature sink, where heat taken from high temperature source, some part of is converted to work, and the rest is been heat is been basically transferred to the sink. So these are operating from if from the high source temperature is T1 and low temperature sink low sink temperature is T2. So the maximum efficiency that we can get from this system heat engine operating between these two temperature range is given by Carnot efficiency. So which is basically mathematically expressed as 1 minus Tc by Ts. Tc is the uh, T2 temperature or the sink temperature, and Th is the higher source temperature. uh, so note that you have to these temperature are given in degrees Celsius, you have to convert it into Kelvin, right? So this will be 273 plus 30, so it will be 303 Kelvin, and this will be 273 plus 800, so it will be 1073 Kelvin, right? So when we'll put here like 303, basically 303 here, okay. And in the higher, it will put this higher temperature. You have to directly put this both value, and then you can get the right answer, 71.76%. I hope this question is clear. um, okay, any doubt in this question? This is basic heat engine question. Okay, moving on to the next question. um, which of the following instrument is used for measurement of temperature? I think a lot of you answered like opted for option B. Okay. So, okay, my mistake again. So this is option B, thermocouple only. Okay. So the correct answer is thermocouple. So basically, in thermocouple you have these two different wires, two different metal wires. So say A and B, they are joined at two junctions. So one is maintained at higher temperature and another is maintained at colder or lower temperature. And uh, since these two junctions are maintained at two different temperature, the Peltier EMF is generated, um, which is function of uh, this temperature of the two junction. So in actual it looks something like this. So where manometer is used for pressure measurement, modern tube is also measured for pressure, and anemometer is used for measuring the wind speed, right? So this is the so thermocouple is the right answer for this question. It's used for measurement of temperature. Now this is the next question. Air is blown over a hot plate of area 50 cross 60 centimeter made up of carbon steel maintained at temperature 220 degrees Celsius. Given that the air temperature is 20 degrees Celsius and convection heat transfer coefficient is 25 watt per meter square Kelvin, the heat loss in watt from the plate will be. Okay, we have a lot of question left. So what I will do is I will quickly start explaining. I also see some have given option B as a correct answer. So the correct answer is option B only. It's 1500. Um, so this is a convection problem where convection heat transfer is happening. So this is your plate, 50 cross 60 centimeter. Okay, 50 cross 60, and this is the area of your plate, right? And the temperature of this plate is given 220 degrees Celsius, and the air temperature is also given 20 degrees Celsius, right? The convective heat transfer coefficient is also given, um, 25 watt per meter square. Heat loss is being asked. So H is given. H is your convective heat transfer coefficient, 25 watt per meter, 20 watt per meter square Kelvin. Area is 50 cross 60 centimeter. Surface temperature is given 220 degrees Celsius. Not to change it in Kelvin, 493 Kelvin. And outside temperature is given 20 degrees Celsius, which will be 293 Kelvin. So we will put all this value into this equation. Note that the unit here is centimeter and here you have meter. So convert it into meter, this area, and then put back into this main equation, the Newton's law equation, Q equal to HA delta T. Okay. When put, then you will get the correct answer, 1500 degrees Celsius. Oh, sorry, 1500 watt. I hope this question, basic like understanding of this question is clear. Now moving quickly to our next question. A 500 kilowatt high power plant running at its full capacity would generate this much kilowatt hour of electricity per year. We are asking for 365 days. Mm, okay, we have only 2 minutes left. So I would like to request you all to stay just for 5 more minutes so we can go through all the questions that I have prepared for this session. I hope it's fine for everyone. Is it? I can just quickly tell me in the chat box. Otherwise, I'll wrap up this session. Okay. Thank you. If anyone have some important work to attend to, what I'll do, I will continue the session for another 5 minutes or 5 or 10 minutes, whatever it will require, and I will upload it on YouTube. Link will be provided to you. You can go back and later and watch these sessions. So I think that would be fine with everyone. Okay. So I have got some answers. Option C. I'll quickly show you the question again if someone has not. Okay. Let me address this question. So the correct answer to this question is option C. Okay, so it's how we'll get to this answer is your rated power is 500 kilowatt. It's running at its full capacity, so 100% of it has been generating electricity. So and it's been asked for per year, so it's for 365 days. So this is for 1 hour you are getting 500 kilowatt, for 24 hour will be 500 into 24, and for 365 days it's 365 into 24 basically. So that will be the amount of uh, generated electricity from this power plant at the rated power of 5 kilowatt running at its full capacity. When you will multiply it together, we'll get the value of uh, option C. Okay. Now, which of the following energy is high grade energy? So very basic question. Um, So I can see option C. Okay. Okay, let's get back to the question. So the correct answer is option C. Uh, that is electrical energy. So basically high grade energy are those type of energy that can be easily converted to other form of energy, so they are more available, easily convertible, and uh, the low grade energy are less available and not so easy to convert, so like heat and all. So electrical is a high grade energy. I hope the logic behind this question is clear. Since we are running out of time, I'll quickly go to the next question also. So it's on the first law of thermodynamics. What is the first law of thermodynamics? So I've just explained it. Hope I'll get quick answer to this question. So I'm getting answer A, right? So the correct answer is answer A only. So as we have just discussed this question earlier, so the first law of thermodynamics gives relationship between the internal energy, heat and work. So internal energy or change in internal energy is equal to the heat added plus work done. I hope this question is clear. We have discussed it earlier also. Moving quickly to our next question. The amount of electricity consumed by a 50-watt bulb for 8 hours. So we have to calculate in kilowatt hour. Okay, option B. C and B. Hmm. Okay, let's discuss this question. So we have been asked about what will be the amount of electricity that will be consumed by a 50-watt bulb if we will be using it for 8 hours. So the correct answer is answer B only. Quite straightforward calculation for it. So your rated power is 50 watt. Your time of operation is 8 hours, so electricity consumed will be 50 into 8, so that will give in watt hour, so unit will be 400 watt hour, but the answer is asked in the kilowatt hour, so we'll divide it by 1000 and then we'll go get the answer 0.4 kilowatt hour. So the correct answer is 0.4 kilowatt hour. I hope this question is clear. Now the collection, moving on to the next question, the collection efficiency of a flat plate collector FPC can be improved uh, by putting a selective coating on the plate, or by evacuating the space above the absorber plate, or by both A and B option, or none of the above. Okay, I'm saying option C. Any more guesses? Okay, let's discuss this question. So we are talking about a flat plate collector. So if you remember, flat plate collector have a glazing material on the top of it through which the solar radiation passes through and goes to the tubes in which your fluid is flowing, right? So if you put a selective coating on a plate, selective coating in term of, it will basically absorb more the incoming solar radiation, or it will provide a evacuating tubes, like the second form that we have discussed, that providing a vacuum between the concentric tube has increased the basically performance of the solar thermal devices. So by opting both A or B method, you can increase the collection efficiency of a flat plate collector. So the correct option is option C. Okay, so this is your right answer. Example of So the next question is example of indirect way of utilizing solar energy. So very basic question. So I'm saying option D also and A also. Right. So let's discuss this question also. So as discussed in this live session also, and in the lecture also, you can see that there are two way of utilizing solar energy. One is the direct, where we have studied the thermal part and solar thermal part and solar PV part, the electricity part. And the indirect way, we have seen all the different method like wind, biomass, wave, and uh, like ocean like waves energy, right? So these all are the basically different indirect way of utilizing solar energy. These all are energy anyway indirectly utilizing the solar energy. So option D is the correct answer. I hope this question is clear. Very basic question. Moving quickly to our next question. So which of the following type of collector is used for low temperature system? So for low temperature system, is it a flat plate collector, or line focusing parabolic collector, or a parabolite disc collector, or all of the above? I'm saying option A. Okay. So as discussed earlier, depending on what temperature you required, so there are different temperature range in which different devices could be used. So flat plate collector around, I think, 40 to 100 degrees Celsius could be obtained. In a parabolic collector, I think less than 400 degrees Celsius, and if we want greater than 400 degrees Celsius, the parabolite disc collector could be used. So for a low temperature system, this is around less than equal to 100 degrees Celsius, enough to boil the water. So for low temperature system, flat plate collector is there to 40 to 100 degrees Celsius. Okay. Now when the sun is at the zenith, the optical air mass is, I think this is the last question that we are going to discuss. um, so the question is asking about the air mass index. So what is the optical air mass value when the sun is at the zenith? So I'm getting option B, right? So let's discuss this question also. So the correct option is option B only. So the optical air mass value will be 1. Now let's understand the question, what it's talking about. So air mass index. So air mass index is basically how the solar radiation coming into the atmosphere is atmosphere to the earth's surface has been attenuated. So as the solar radiation travels through the atmosphere, there is also absorption and scattering of the solar rays as it travels through the atmosphere. So there are several gases like CO2, water vapor, and also very fine aerosol particles, so that leads to scattering and absorption of this solar rays as it passes through the atmosphere and reaches to the surface. So optical air mass gives about tells about how much this attenuation has been taken place in the incoming solar radiation. So in mathematical terms, it's so if solar radiation has basically this is the direction of solar radiation, uh, and this is the uh, place we are talking about. So the air mass ratio m, denoted by m, will be your ratio of s2, this length of the propagation of this incoming solar radiation to the point, to the basically your vertical distance, or your the minimum distance through which the solar radiation has to be that solar radiation can travel. Okay. So in term of beta, it could be written by 1 by sine beta. So as told earlier, as sunlight passes through the atmosphere, less energy arrives at the earth's surface. So here, if you are talking about the zenith means directly over it. So the sun is here. So if the sun is here, then your basically air, okay, this is your sun. So your air mass ratio will be 1 only, so it will be h1 upon h1 only, so your ratio will be 1. Am zero air mass ratio, 0 means we are talking about when there is no atmosphere, or we are talking above the atmosphere. the basically your extra terrestrial region, beyond terrestrial region. So there the air mass ratio is 0, and air mass ratio of 1.5 is the assumed average at the earth surface. So all the calculation you do for the solar panels or solar cells, so you there you consider air mass ratio to be 1.5. So that is the practical application or understanding behind the air mass ratio. So the correct answer is option B, 1. And I think this is the end of today's session. I hope this session was useful to all. Thank you for listening. We'll connect again at the same time next Monday. Hope you will all join in that session. And if you have any doubt regarding this session or any doubt regarding the lectures that has been provided for week 1 and week 2, you can directly mail me or directly ask on the discussion forum. We'll be very happy to clear your doubts. And this is all for today's session. Thank you all for listening. Anyone have any doubt? Okay, I hope it's clear. Okay, meet you guys in the next session. Um, Thank you all. Uh, if you have any feedback, also you can write back to me or you can tell me in the next session. I'll pay attention to it. Okay, uh, I'll end the session now because we are way beyond our time. We'll meet you in the next session. Okay, thank you all.